Hey, Mike Panaki here with Network Protocol Specialists. And I thought I'd take this opportunity to spend some time talking with James Kahkoska, the Chief Technology Officer at NetAlly, about the Landbert application. What we're going to see is Landbert allows us to go in and qualify media for running different data rates. So I'm going to bring James into the stream here so that we can start talking about Landbert and why we want to qualify media and all of that. James,
Hey, Mike.
welcome.
Thanks. Hey, Mike.
So, James, so people know, what is it that you do at NetAlly?
So at NetAlly, I'm the Chief Technology Officer, but I've had a variety of roles in handheld network test back to 1995. So that's my current position, though.
Fantastic. So we'll just jump right into it. What benefit does Landbert offer somebody that has an existing infrastructure?
Yeah. Well, what it really lets them do is qualify their media in a pragmatic way, in the way in which it will be applied, uh, as opposed to using certification as kind of a proxy for the media linking and carrying traffic at that speed.
Okay. So if I have an existing Cat5e link that has been working just fine, why would I need to qualify it?
Yeah. So certainly the biggest driver in this space is trying to use that same cabling for newer devices, particularly APs, access points. And as access points have gotten more and more sophisticated, they have more radios. They have sectors and things like that. They are requiring more power, and so and also a higher speed. And so on the higher speed side, the IEEE introduced N-base-T. That's a 2.5 and 5 gigabit speeds across existing media. And it's actually the first time, if you think about how Ethernet has just constantly gone up, right? 10 to 100 to gig to 10 gig, and now, it's generally gone up by multiples of 10. And so it's actually the first time that the industry, the IEEE, kind of tapped the brakes and said, whoa, hold it. We've got 90% of the media installed in the world is this Cat5e cabling. We just want to run it at a slightly faster speed. Let's try to go backwards a little bit in speed. And so they did these tweener speeds between the existing 1 gig standard, which had been around 20 years, and the 10 gig standard, which had been around for 5-6 years, and introduce these intermediate speeds, 2.5 and 5 gig. And that is enough bandwidth then to kind of feed the new access points, because what they're really saying is, the Wi-Fi is now capable of doing over a gig, and
Right.
so you need a backhaul from your APs to do more than a gig.
Okay. So I've got these technologies. I want to be able to support an access point or really any other device that supports N-base-T. I want to use my existing cabling. So why not just put it on there and find out if it works?
Yeah. So what we've discovered in a lot of our testing is that first of all, it may work, but you don't know how close it is to the edge. So and really running these higher speeds over the cable is largely a signal to noise ratio game. They're trying to see, they're just pushing the limits of the SNR that's required using digital signal processing. And so they can so you plug something in, it might work, it might not work. What we've discovered, though, is there's a lot of, since it's running on this razor thin signal to noise ratio, any noise will affect the signal, will affect good data transmission. And so we've just seen a lot of cases where noise, impulse noise, ESD, motors turning on and off, static discharge, even mechanical noise, cables getting moved or vibrated, is enough to cause signal distortion. So one of the nice things about Landbert is it's just sort of you can do a long-term test, like a 24-hour soak test, hook it up across a piece of cabling, and have some, and also we'll show you the signal to noise ratios on all 4 pairs. So you'll have a sense of, what, I've got pretty good margin here, good enough margin. I ran trillions of frames over it bi-directionally for 24 hours. It must be good. I don't need to I don't need to pull new cabling, because the reality is it can be expensive, in some cases even prohibitive, to pull new cabling. You can spend far more pulling cabling. Think about going into walls and ceilings and things like that, insulation, whatnot. And so, let alone sites where it's just kind of, might be historically prohibitive or just incredibly difficult. Think about a warehouse or some large open space where you need to, get up on scaffolding and such. And so it can be quite expensive to pull new media. And the reality is, there's a really good chance that the media you have will pass the trap just fine, and that you will never have an issue. The analogy I always use is when we moved into our house, there was a telephone line, and all we had was telephone pot service. The cable that was pulled up the street, whatever, 30, 40 years ago, was just for voice, right? That's 4 kilohertz kind of bandwidth, and then and along came modems, 300 baud, 1200 baud, 9600 baud, and on and on, and now I can basically run DSL at many megabits, and so that's just advancements in digital signal processing, and the cabling hasn't changed, right? It's just
Right.
that the processing has gotten better about pulling the signal from the noise. And so that's also what's happened on the Ethernet side. Is basically the PHYs have gotten so advanced at pulling the signal to discriminating the signal from the noise, that they will run over media that you would be told, using traditional certification methods, that you can't do that.
Okay, and that was going to be one of my questions. Is I have certification equipment. I can go in and say, will this support 2.5? But are there cases where my certification tool might go in and, following that strict set of rules for how that cable needs to perform at various frequencies, are there cases where that could come back and say, that's not going to support it, where we find that when we run Landbert, it will?
Absolutely. We've seen that in case after case, where we've taken media, it tells us it wouldn't carry 2.5 gig, and we have no problem then even putting 5 gig over it. And so there's just like I said, there's a vast difference between what the certification numbers will give you, because what they're really saying, first of all, they're using a different methodology, right? They're not actually using the actual manufacturer PHYs. These are companies like Broadcom and Marvell, and so they're kind of doing this parametric frequency proxy noise crosstalk, but they have no idea how much the industry has advanced in terms of actual signal noise. Back to my modem example. And so yeah, there's just a lot of times that certification will tell you it'll fail, and then interestingly enough, we've seen the converse. Since certification is sort of a race to how fast can you certify, right? That's how all the vendors, that's their key criteria. And so that's what's not going to be a 10-second test that you're looking at the line during.
Right.
What we see is that it's when that motor turns on every 20 minutes, or it's a static buildup on a somewhere conveyor belt. There's people getting in and out of chairs, even, believe it or not. It's a mechanical noise. It's just a noisy world, right? And so there's a lot of noise sources. And so what's really nice about the Landbert feature is you literally can 100% soak that media. I mean, we're sending just back to back frames the entire duration, whatever you choose it to be. You could do 5 minutes and send millions of frames. The reality is, in 10 seconds, you can send millions of frames, right? 10 gig
Yep.
is so fast. And so, or you can let it run for 24 hours. And since we trend all the information, you might see that, wow, every 40 minutes, there's a lot of ability to see what's going on in your environment, because you might see every 40 minutes there's something that's turning on. Well, that's some sort of an impulse thing, or there's some blast, or there's something turned on that was on for 20 seconds, or whatever. Right? So we have this 1 second granularity at which we're measuring to see if every packet came through, and if they came through error freeze or with a CRC. And so it's just a pragmatic way to put the rubber to the road and test the link, while also providing you with signal to noise information and sort of trending error information, so you can kind of diagnose what's going on. Anyway, the answer is we've seen both. We've seen both where the cable tester will tell you it won't carry it and it can, and we've seen where the cable tester will tell you it's fine, and because it's more of an impulse noise or some sort of a environmental thing, there's actually an issue.
Well, and one thing that I thought was interesting, and we're going to get to running some tests and so on, but back here over my shoulder, I've got a coil here of 100 meters of single mode fiber. And, I can't resist buying cool things. And so I saw on Amazon that there were these bi-directional transceivers. So they are SFPs and fit into a regular SFP slot and act like a regular SFP. But one of them transmits at 1550 nanometers and the other one at 1310. And so it's sending these two wavelengths in opposite directions through a single fiber. And they say I can do full line rate, full duplex gig over a single fiber. So if I've got a situation where maybe I need more than one link, now I could take two fibers and turn it into two 1 gig channels. So one of the things I used Landbert for was to find out if it really did that. Well, if I'm just using a cable tester, as soon as I hit that first transceiver, I'm dead. But Landbert is sending frames, correct?
Yes.
So this way, I can pass through those transceivers. I can go from copper to fiber back to copper, and have a reflecting device on the other end. So it seems like it would allow me to test some more complex configurations than what we have with just something like a cable tester.
Yeah, absolutely. So another nice thing about Landbert is it's media agnostic, and so we talked about so far on kind of the wired side. Well, its peer there in terms of certification would be the cable certifier. But
Right.
but you'd have to buy a specialized tool just for cable testing, right? And then to do optical testing, you would have to buy literally a separate tool or a completely different test module, right? An OTDR or an OLTS, but you would need specialized optical certification equipment, very, very expensive. The nice thing about Landbert is it'll run over copper out the RJ, or it'll run out literally any SFP you want to put in there. So another nice thing about this is not only are you testing the media, the fiber itself, but you're also including the SFP. So you're kind of basically running over the entire link, if you will, as it will exist when it's deployed. And what's fascinating, of course, is how many different SFPs there are. Right? There's a litany of them, but the ones you're the SFPs in particular is the bi-di, right? The bi-directional.
Yep.
They on the same fiber, they can pass light in two different directions because they're two different frequencies, and it's phenomenal. But Landbert is agnostic to the SFP. If you think about everything that goes in SFP, because you could have direct access cables, optical cables, traditional SFPs and fiber, single mode, multi-mode, LX, ZX, SX. You can go from top of the rack 2 meters, out through 80 kilometers, right? If you look at a ZX SFP, and so across a metro. So nice thing about Landbert is that the same tester that you might be using for qualifying your internal wiring, you can also use then for qualifying any fiber, any link, anywhere in your enterprise.
Well, and so you bring up another really good point, and that is I was talking to a customer last week, and they said, hey, we're looking at what equipment we need to get. And so they're in charge of the infrastructure, copper, fiber, et cetera. So they work with the networking group that's responsible for the switches. So one of the discussions that came up was, where's the demarcation point between where the infrastructure cabling folks end and where the networking people begin? And one of the things in their environment that we kind of came up with was it ends at the electrical interface of the SFP. So from their group, the networking group's standpoint, they are responsible for everything on the electrical side of the SFP. So one of the things that I've seen that's been kind of neat with Landbert is it allows me to validate not only the copper and fiber infrastructure, but I'm able to validate the SFPs that I'm going to be putting into production. Because I mean, you're the one that is the mastermind behind the EtherScope. I mean, every SFP I've ever plugged into it, or DAC cable, it seems to deal with those okay.
Yeah, because there's this MSA, multi-source agreement, is wonky of a acronym as that is, but there's this spec for that electrical side of the SFP, right? SFP is, well, here, SFP, and so here's the optical side right there, and then here's the, oh, sorry, the electrical side right there, right? See those pins, those contacts. So what you're saying is responsible for the fiber coming in, it terminating the SFP. There's no dust, no, it's a clean termination and all that, and that basically the network side will pick it up from these pins. So yeah, that's it's kind of interesting because is kind of the parallel of that is on the copper side. You can include the patch panels and the doing the same thing. I would assume would be, well, the network guys are responsible for the patch cable that plugs from the patch panel right into the switch, right where it comes into the switch would probably be the demarcation point for responsibility. And once again, Landbert can run through a patch cable and a patch panel and out through the horizontal cabling, and you can even go out to, let's say it's a cubicle that RJ mounted there, put another patch cable on it and say, hey, can I run gig traffic over this for whatever period of time. So yeah, there's just a lot of it. It's just a super versatile way to understand it if there's any issues with your media carrying the speeds reliably.
So Andrew's got a question, and that is, excuses, and there's no ignorance there, Andrew. I mean, this is why we're doing these things. But how does Landbert differ from doing iPerf testing? Why can't I just get a couple of Linux? I can get my Raspberry Pis to do 992 megabits per second. So why don't I just throw a couple of devices on each end and do an iPerf test?
Yeah, it's largely, good part of it is in the simplicity, right? So you could run an iPerf test. You wouldn't have a sense of signal noise. And as Mike says, with high enough performance, you could probably get a reasonable amount of frames across. So you might struggle though to do N-base-T qualification, right? 2.5 gig, 5 gig, and so and you won't have the monitoring quite at the same level. The other problem is to run something like iPerf, you need to kind of, it runs at the IP layer, right? At the UDP layer, and so you need to have other things there like DHCP addresses, right? So either you need to take your endpoints and then go through some shenanigans to assign static IPs and subnet masks, and maybe they get a little bit hung up because then suddenly they can't talk to a gateway or a DHCP server or whatever. And so you need those two units then sitting there and running and then linking, connecting, and then run the iPerf system. It's a lot of, some of it's just in the degree of automation, the support for multiple media such as fiber, and then truly running at 100% saturation rate. Another thing, we allow random frame traffic and all that. I think the other thing about I think iPerf, when it does UDP, I believe is only unidirectional. So either you're running a TCP where you've got the asymmetrical axe coming back at a lower rate, right? The one thing about Landbert's basically both transceivers on both sides saying, hey, I'm going to blast full traffic at whatever rate you said, 10 gig, 5 gig, whatever, and just full duplex, 100% line saturation, run those through. And so, and then lastly, iPerf, you'd have it might be tough to, certainly on a Raspberry Pi wouldn't be able to do fiber and things like that.
So what is, I mean, I haven't, you know me, I mean, I haven't thrown a tap in there yet to look, but what are you sending across the wire when you do a Landbert test?
Yeah, they're fairly low level frames, right? Because there's no IP addresses, and so they're just sort of there's some MAC addressing, and then randomization of the contents of the packets. You can also pick your frame size. Another interesting thing about Landbert is you can pick the frame size, and kind of what you're trading off uh, is sort of error granularity. We tend to steer people towards testing with 64-byte packets, because if there's any bit lost anywhere in that 64-byte packet, that's considered an error, right? This
Right.
is not bit error rate testing. This is sort of packet error rate testing. And so the smaller the packets, the more granularity you'll have in terms of detecting those errors. And so, but that said, you can go up to 1500, I believe, even jumbo 9600-byte packets if you would like to.
So, and we're gonna, I know people are probably interested in seeing what this looks like. So I'm going to share my screen here in just a second. But one last thing before we do that, and that is, I've got Landbert running on my EtherScope. What do I need to have at the far end? Can I just
Yeah.
loop the fiber back? Can I? Do I have to have some other NetAlly tool on that other end to be able to loop it?
Yeah. Yeah, so you need at least one master, right? And that could be an EtherScope or a link runner 10 gig. Uh, and then at the far end, there's a variety of things you can have at the far end. And let me start at the slowest speeds, because that'll be the easiest. If the media you're testing over is not full duplex, if you think about two strands of fiber, one's dedicated to RX, the other one's coming back with the TX. Those are two separate things. You can loop back that media at the far end. So you can just literally use a cheap couple dollar. In fact, you can make one. You can take a fiber patch cable and just rip it in half and basically make a simple loop back. Now, what you've done is you've increased the length to 2x. That's often
Right.
not a problem with fiber, right?
Yeah.
So you've got that. The other case of half duplex transmission over the media would be 10 or 100 megabit Ethernet. And in that case, 1, 2, 3, 6 are being used independently for RX and TX. And so there you can also loop back pin 1, 2 to 3, 6 and create a loop back. So
Got it.
if you're only testing 10 or 100 megabit copper, or you or fiber, and you want the lowest cost way to deploy this, you can just use loopbacks on the far end,
Got it.
and those are readily, you can buy them, right? They're readily
Yep.
available on the market. Then you get into the active testers. So basically we allow you with the link runner G2 to do 1 gigabit
Okay.
loopback. It basically has a reflector that'll support that. And then going up, if you want to validate it at 2.5 gig, 5 gig, or 10 gig, you would need an EtherScope or a link runner 10 gig on the other end.
So how about a software I can use the software
Yeah.
reflector with the performance test. Could I
Yeah.
use a software reflector with Landbert?
No, you can't, because we're basically doing this at a very low level at the physical layer, right? The software reflector is up at like layer 3, and you're addressing it with an IP address, and then at the software layer, we have an application that's sitting here saying, oh, I see a packet. Oh, this looks like one of mine. I'm going to flip it around. Whereas to do the amount of traffic that you want to do with Landbert, you need to basically control the PHY very, very deliberately.
So Nick D asked about, what about MTU? Where does that come in with this? Do we need to worry about MTU in the case of doing Landbert?
Yeah, it's a good question. You don't. I mean, the only reason it matters is, as I mentioned before, the shorter frames will detect at the end of the day, we're looking for a frame to be lost, or we're looking for a frame to be impaired, right? In terms of a bad
Right.
checksum. And so, so the shorter the frame, the smaller windows that were, are you okay? Are you okay? Are you okay? Are you okay? So you can go to longer MTUs. Typically MTUs are more worried about the top end of the range, right? Well, this past jumbo frames, 9,000 or 1518 or whatever 1488, and so, but generally this is a media test, and so. So it really shouldn't be there. There'll be no equipment in the middle that has an MTU sensitivity like a router. Uh, so if you have MTU needs, it turns out the same products that, and one of the things that really differentiates us in the market is so we're just talking about Landbert and media test today. We've got a whole nother application on top of that, which is layer 3 UDP-based performance testing, right? And that's,
Right.
you can do 8 different streams, you can dial in QoS levels, you can target 8 different endpoints, you can target 8 different QoS levels over the same link or anything in between. That'll run up to 10 gig. It characterizes latency, jitter, loss, right? That's for testing across routers and enterprises and WANs and software-defined WANs and just has a lot of applications. In fact, I was talking to a customer yesterday. It's the telecom group that wants to that basically they've got their own responsibility and they want to and they're having issues with, I'll say, the transport group or the network group, right?
Right.
And so they basically are looking to that layer 3 test to do performance testing from site to site to basically say, hey, look, it's a transport problem. It's not a VoIP problem. So there's a lot of applications for for our traditional performance test. We also call it line rate performance test, but that's largely about service level agreements and all that. But the nice thing is you have the same tool that can do both, right? You can either validate media using Landbert, or you can validate your WAN links. Yeah.
Well, and I think that in talking about we could do a whole nother session on that one, right? Because in that case, we are really putting pass fail, parameters on there. And we can, I've in the past doing the performance test, I've done packet captures to get an idea of what the packet size is on the application, what the data rate is. So we can create profiles with that really represent particular applications and then send those through.
Yeah, that's a good point, because in the previous case I was just describing, they want to send something that looks, since it's a VoIP group, it's largely RTP, right?
Right.
Which is the voice packets, and so well, those tend to be based on your codec, about 110 bytes, right? Because they're coming every 20 milliseconds. That's your voice encoded, and so in their testing, they will set their frame sizes to 110 bytes to kind of roughly emulate the RTP packets that they're most concerned about.
So I'm going to go ahead and let's bring up my screen, and we'll throw that up there. So what we have here is we've got, well, in fact, I can switch over. Let's see. I'm not sure how that camera's aimed right now. Move that over just a little bit, but we've got a couple. We've got a EtherScope NXG, and we've got a Link Runner 10 gig, which the Link Runner 10 gig is really just the EtherScope NXG without wireless, right?
Correct.
And so I've got 3 of these up on the screen. So what I'm going to do is I'm going to go ahead and click on the Landbert application. And I mean, one of the cool things, I think, with the EtherScope NXG and actually Link Runner G2, EtherScope NXG, and the Link Runner 10 gig, it's an Android platform. So, I mean, you guys with Landbert, I mean, that was writing an app, right? I mean, it's not like you had to build a whole nother tool to support this.
Yeah, that's right. I mean, and sort of from a not for do a shameless plug, but from a protect your investment standpoint, when EtherScope came out, it didn't have Landbert, it didn't have that air mapper, it did, which is Wi-Fi survey, right? And so we just continue to add apps to build out new capability. Think of it as, Signal is already a Swiss Army knife, so we're just adding other, blades to your knife, right? But that's just coming along on the existing hardware. So Landbert, basically, you could have bought an EtherScope a year and a half ago, having no idea this is even coming down the line, and suddenly you got this great new capability to test media in your enterprise.
So we've got the EtherScope NXG and the Link Runner 10 gig. So EtherScope on the left, Link Runner on the right, are plugged into 247 feet of Cat5e cable. I've got coiled up. It's nowhere near your cable coffin you guys have, but it's my mini cable coffin. So I'm going to put this into loopback mode. So I'm going to put the Link Runner 10 gig in loopback. I'm going to hit start on that. And I'm going to come over here and let's change our duration to 1 minute. I don't think we want to sit around for 10 minutes. And also.
So, one of the things about this test, back to the iPerf question before, is just this sort of drop dead simple, right? You basically say, link it your fast, in general, you won't even have to touch the settings. You just basically run one in loopback, run one in as kind of the master, the generator, if you will, is what we call it. And so, and away you go, right? There's no fuss. We take care of all the linking and all that other stuff for you.
All right, so we'll see if it sticks with it. So here we linked at 10 gig, and it looks like we sent a few frames.
Yeah, so those were kind of our probe frames. I'm not sure what's.
So I think in this case, this cable could be right on the edge of where it thinks it can link at 10, but it just can't quite get 10 to work.
Yeah,
and so what we may need to do, and if it doesn't link up right away, I'm going to force it to 5. Let's give 5 gig a try. So we're going to come in and we're going to say we're going to do 5 G-base T. We'll go back and let's go ahead and start that. There we go.
There we go. Yeah.
All right. So what are we seeing here, James?
So what we're seeing on the right is the loopback unit and it getting frames, and you can see we're clicking along there. This is a 30-second test. At the top, we're showing you, hey, but we were getting every speed advertised, including 10 gig, but we could only link at 5 gig. Anytime we don't link at the fastest advertised speed, we give you a warning. So that's what that yellow dot is indicative of. But now you can see, in fact, that test is considered a fail. And so that said, linked at 5 gig, as it did, basically we sent 213 million frames, back and forth, completely error-free. The far end unit, you can just leave it. You can just leave an auto, right? It'll.
Well, what I was going to do is set it to 5 so that's all it advertises.
Okay.
Because without losing any frames, it'd sure be nice to show that we passed.
Yeah, good point.
Right. So we'll see if. So now we're just testing at 5, and yeah. So it's 64
I've never actually tried
frame.
that. I'm glad it worked.
I've tried it before.
Yeah. Okay.
Yeah. You know me. I mean, I love to do live demos. And get out there on the edge. But
and if you scroll down a little bit, let's show the signal and noise stuff. You can also see then as it's running, we show you a couple of things. So a channel is basically a pair. So there's 4 pairs, A, B, C, A through D, and then we measure the delay skew, which is the difference between the pairs, and so the most delay skew is 2.5 nanoseconds. That's on the B pair. At the same time, you can also see that the SNR is lower, right? There's less margin on the B pair, and we see this quite often. The B pair seems to be the dog pair, and I think it's that one pair that tends to wrap around the cable more. Right, so it's typically even if you were to take out a very precise TDR and measure it, you'd see that pair, the B pair, tends to be longer, and because it just has more pair twists, not inner pair but outer pair. So basically, as we're running along here, we're monitoring the signal noise ratio, and this isn't bad. In fact, our default signal to noise ratios, if it would drop, I think, below 5 dB, we would have considered that an error unless you changed the settings. But basically, so there's so we can fail because we don't link, because basically we can't get the units to link at the speed that you're trying to. We could fail because, hey, we linked, but we also had the SNR didn't meet the threshold, or we could link and fail because we didn't pass some sort of an error threshold. In fact, if you go to the settings on the master on the left, you'll see, I think, the 3 thresholds there. Yeah. So you can grade based on, if you want the perfect media, you say, I want no errors, right? But you can basically do percent or count, and you can also isolate those for loss as well as just errors. So there's a lot of ability to control the grading, and back to what's driving the yellow. So you can basically determine that. But out of the box, you don't need to mess with it. We have all those pretty good defaults for you.
Well, here's one other thing to keep in mind, and this is why we see a lot of Cat6A patch cords fail, is when you look at the construction of an RJ45 jack, that in many cases, the B pair, and we can validate this, is going to be in the 3/6 position, and it is straddling the C pair.
Good point.
And so that pair, we've taken that twist and we've wrapped that around that other pair. And that's where we see a lot of times that Cat6A jacks will fail the near-end crosstalk test right there. And where a lot of these field terminated jacks that we see will pass because we're crimping the conductors down, and the printed circuit board has a better routing for that. Be interesting to test a cable that had the had a field terminated connector, like for an MPTL link, and see how that compared to just a regular patch cord.
Yeah, it's kind of interesting because sometimes this is a little sidebar, but sometimes I feel like almost a whole line of tools, right, testers and issues were created because when they first did Ethernet, they didn't just go 1, 2, 3, 3, 4, 5, 6, 7, 8, right? And the pairs were all lined up, right? The whole issue with 3, 6, and a number of people that have built, bad patch cables and things like that, and the issues even down to this B channel that it's introduced, and it was largely because I believe all the way back to the RJ11, they had basically used a tube in the middle, and then when you did line 2, they went like that, and so there's just this weird legacy where they held on to this, and so, like I said, to this day it almost created a small test industry in and of itself, just because the number of issues with people knowing that needing to know that it isn't just a natural pairing order as you would expect.
So let me I've got some shielded Cat6A, and that's one of the things that you mentioned was mechanical. I mean, we showed that this Cat 5e that I grabbed out of the box works just fine at 5 gig. Now, one thing that we have seen, it'd be an interesting test to do. I think I might be one device short to do it, but and that is to put 2 Cat 5es next to each other and do Landbert on both of them, because that's where we see our alien crosstalk come in. And it may work with one link, but going in and running Landbert next to a cable where it's already running would be interesting. Let me grab some shielded Cat6A cable. We're going to run this again, and we're going to bend some cable.
All right, you do that, and I think yeah.
All right, so let's give this a try. We've got some shielded Cat6A, and what I'm going to do is this has some of the field terminated connectors on it. So let me zoom out here just a little bit. And we're going to unplug our cables. I'm going to plug that in. I'm going to plug that in there. And so I'm going to go ahead and hit start again on there. And I'll tell you what, let's stop.
You know, we might want to go back to auto to get 10 gig.
Yeah, let's get 10 gig. So I'm going to come over here.
Yeah. You know what I was going to say is, alien crosstalk typically is more pairs in a bundle than just one. So I don't think running 2 cables side by side would necessarily be enough. It's, I think it's more of a bundling effect.
Right. And also another place that we've seen a lot of alien crosstalk originate is in the patch panel.
Yeah.
In fact, more so than in the cable.
Interesting.
All right. So we're going to start our endpoint. We're going to start Landbert. Start running some traffic through there. So we linked up at 10. No error. So I'm going to come over here. We're going to bend this cable a little bit here. Let's see.
Wow. Good error.
There you go. We'll get my bald head out of the way there. Let's move these back. So if we start moving this cable around.
Yeah, so you can start to see how, we're basically measuring the traffic every second. And you can see that we're seeing errored frames. It's a real-time display. And you can run this, as I mentioned before, up to 24 hours, right? So it really can be a true soak test of, is there a problem with, I don't know, the floor buffers at night, or some particular piece of machinery turning on, or anything like that. And so could be a conveyor belt moving, that's causing some mechanical noise on the line. It's just, basically they push the margins so tight on the number of levels. We don't have a slide for this, but if you think about old 10 megabit and a 5-volt swing, that was a 0 and a 1, right? And then when they got to 100 megabit, they went to an MLT3 coding, right? So suddenly there were 3 different levels of discriminate. Same voltage swing, let's say 0 to 5 volts, but now there's 3 levels to discriminate. Well, then when they got to gig, it was PAM5. Now they were trying to differentiate, 5 levels, same voltage screen. So you think about it, every time you do that, the amount of voltage between, gets narrower and narrower. Well, when they invented 10 gig Ethernet, they went to a PAM16 encoding. So now there's 16 levels in that same voltage swing that just used to be a 0 or 1. So now there's 133 millivolts between every discernible level, right? And that's where the PHYs, the DSPs, have gotten so much better about pulling all that out. And then when the IEEE hit the brakes, what they said is, okay, we know this PAM16 coding is working pretty good. 10 gigabit, wired Ethernet had been around for 5-6 years and was performing well. What if we just slow it down and keep the same levels but cut the clock speed in half, right?
Right.
And so that's where they brought the clock speed down to operate within the bandwidth of the cable. And that's basically how they achieved, 2.5 gig rates over media that didn't have the same frequency characteristics.
And what I think is interesting is we've done this kind of test with bending the cable, and we don't see the same issue with unshielded. And it has to do with how that cable interacts with that shielding and everything, and how that signal gets reflected back. So here's a case where we would expect shielded cable would perform better. But in a case where we have movement in the cable, we actually see errors. And with industrial environments where we see that maybe there's a machine that could be moving. I've got a fluorescent light over there that we've hooked up and to the oscilloscope, or hooked an oscilloscope up to the cable before, and you could see the spike on there. So I don't think we have time today to drag that out.
What's interesting is in some of these studies that the NBASE-T IEEE committee did, they did it was a lot about ESD too. And so basically in a library, depending on the type of chairs, They were measuring from like literally 10, 15 feet away was enough of an impulse through the air, an electrostatic discharge, as people getting up into and out of chairs, that it could disrupt the traffic. So you just never know what it's going to be, right? It's just a noisy, staticky, world, and so that's where Landbert is just really good about saying, okay, I'm using real files, just like the real equipment, right? And it isn't that there's anything special from a test equipment manufacturer, right? We're using the same files. At the end of the day, there's only a couple of five vendors, right? There's Broadcom and Marvell and maybe one other, but basically they're the two biggies, and those are the files you're going to find in all the gear. So we're not, it's so if it works with Landbert, it's basically going to work with the gear you have.
Well, and that's, I mean, and I guess one of the other ones from a troubleshooting standpoint is if somebody is complaining that things are slow, we went back and we took a look at the switch stats and we saw, or even with, I mean, I did a webcast this morning on network discovery. If we went in and the health check feature and discovery on the EtherScope came back and told us that we were seeing FCS errors on a switch port, we could take that connection, disconnect it, put Landbert in there and run it for a period of time so that we could see, like you mentioned, is there a time period that we see a spike in that? And I think that's one of the things with other means of qualification is that those are a snapshot in time. And you've mentioned this over and over again in this presentation, but that is that here we can run it for 24 hours. And as we see as we saw on the screen, I took the screen away. Let's bring that up again. As we see on the screen, we've got our graphs over here, and we can change the granularity on that so that we can look at over the whole time period or really zoom into a particular time to see if are we seeing that. Why are we seeing those FCS errors? When are they occurring?
Yeah, in fact, if you were able to you can double tap like on that peak there and even zoom in, right? I believe. There you go. Yeah. So yeah, a lot of ability to kind of observe the trends over the 24-hour period. What you were just mentioning made me think, and that's one of the nice things about the EtherScope, right? Is you could just be doing regular network testing, and we're sitting there and we're monitoring your switches, and all of a sudden we're like, boy, port 17 on this switch just continues to have errors, and so go out, pull pull that link and put a couple testers on, put a tester on each end, run Landbert for some period of time, and determine if it's the media, right? Because if it's not the media, then there's got to be something wrong in the switch, right? Almost got to be a bad transceiver or something. So yeah, just kind of, we always try to strive to have a complete workflow, right? It's one thing to say, aha, we saw this, but to let you go to the next level and kind of parse out the space. Hey, this is truly, do the triage, right? This is truly a media problem, and I can prove it. As opposed to, well, I don't know, there's something wrong on that link. We keep getting errored frames across it. So it really just lets you take the workflow to the next level.
So I'm going to, before we wrap things up here, I do have a couple of fibers that I connected up. I've got a bunch of old OM2 fiber. And so I'm just going to plug in I plugged in the fiber connections on top of the EtherScopes and the Link Runner 10G. So I'm going to go ahead and hit start on here. We're going to hit start on here.
Yeah. So what you'll see is the top of the screen kind of all stays the same, right? This is a fixed speed and all this stuff. But at the bottom, we're basically pulling out all the DDM information out of the SFPs that you would actually be deploying, right? So you can imagine you can run this for 24 hours and know that, hey, the thing didn't get too hot. My TX power is good, my RX power is good, and things like that. And so it's just really nice to be able to kind of soak test those SFPs along with the fiber and really make sure. I mean, the reality is, SFPs more, you practically have a coffee can of them, right? And it's like, oh, I need to deploy a new piece of fiber. And you're reaching in, grabbing these SFPs. How do you know if they're good or bad or why they ended up in that can in the first place? And so, so having these SFP details at the bottom. So we basically, depending on the media, right? As you remember on the copper side, we showed you the signal to noise and delay skew. That was largely about the pair characteristics. But the top stays the same, right? The methodology is the same. The grading is the same. Blast traffic at full line rate, look for errors and loss, and show you that in a trending manner all the way up to 24 hours if you choose to.
And so this is great. I mean, assuming, I mean, we see some variation with the SFPs and the accuracy, but I mean, really, if we're looking at the EtherScope is transmitting at 2.54 decibel meters, and we're receiving 4.6 decibel meters on the on the Link Runner 10G, we're seeing, about, well, a couple dB of loss across that link. Now, a lot of times what I'll do, and this is a feature that you added in for me actually, is to go in and use the set reference where we can measure at the switch and then go measure at the other end and look at the difference using the same SFP. But I mean, if we went and looked at the specs for the receive sensitivity on these SFPs, we'd find out, hey, 4.5 and 3.56 are pretty darn good numbers for those SFPs. Now we're probably looking at a couple hundred feet of fiber here, so
yeah,
not much.
Yeah, barely pushing it, right? Because I think at 850, it's 2 kilometers. No, it's I can't remember, but anyway.
Yeah. Yep. Yeah. Well, so with 10 gig, 10 base, 10G base SR, we are limited to 400 meters of OM4 fiber. And, but one thing that was brought up, and just to recap real quick, one of the biggest differences that we see with Landbert and a typical method of qualifying or certifying cable is Landbert's taking the digital signal processing into consideration as opposed to just looking at the wire, right?
Yeah, that's true.
And as you mentioned,
it's kind of interesting because since it's applied also, you're not, what's always interesting is trying to read the sheathing, or you grab a piece of fiber and there's some fine silk screening on a piece of cable, and how they're labeled and having the decoder ring, and what this really says is, and as you know, Mike, the cable that you get from a vendor one month may look different, 12 months later. There might be some manufacturing tolerances or things like that, and so it's nice to be able to basically not have to look at any of that labeling or sheathing. Just, these are the SFPs, these are the fibers I have. I'm going to plug it together and see if it'll carry the traffic. Very practical.
Yeah, I mean, it's fun. It's fun stuff. I'll tell you what. Let's do one last one because I can't resist, and that is unplug the fiber. We're going to plug in the link going through those bi-die transceivers. So let's run this through a single fiber. So we're going to come into this EtherScope right here. We're going to fire up Landbert on there. We are going to hit start, and we're going to come over to this one, and we will hit start. And these are connected to 1 gig transceivers, so we don't expect it to do more than 1 gig.
Oh, you're in generator. You need to be in loop. Oh, there we
got go. It. So it's good catch there.
Yeah, and we've got some safety mechanisms in there too, like when we won't let you blast your traffic into a switch or things like that, right? We make sure you've got these units end to end, and that you're not going to accidentally blast out a network.
Right. All right. So there we've got loop back. We've got just make sure I've got this plumbed up correctly. I've got link.
Let's see, waiting for loop back running.
Yep. So there is something I'll have to Well, that was kind of a. There we go. Bad connection.
Oh, good.
The connection was loose on the single mode fiber on one end.
Nice. There you
And
go.
so I pushed that in a little bit, and I didn't do that on purpose. That wasn't a on purpose demonstration there, but now we've got it going through, and we see that we are doing full duplex, full line rate, 1 gig through that single mode fiber. I need to order a big old spool of bare fiber. They say that this is supposed to be good for up to 20 kilometers.
I think with ZX you can do 80 kilometers.
Yeah.
On your
with the Bi-Die.
Yeah,
so
yeah.
that's,
Yeah,
I mean, that's
amazing.
enough that I could start my own little ISP here or something.
Yeah.
Run fiber through the ditch out in front of the house.
Yeah, I mean, well, either you get double the bandwidth, or gosh, just think if you had like one pair, if you had a couple of fiber strands and one of them was bad for some reason, suddenly you can get back that bandwidth just because of the miracles of multiple wavelength modulation.
Well, that's we had a school district we were talking to one time that the ISP, I think they were being mean. They gave them one fiber for free. And I think that they thought that they were being smart by, kind of forcing him to buy the other one.
Yeah.
And they went to wave division multiplexing and used that single fiber. So the joke was on the ISP.
Oh, brilliant.
All right. Well, it's almost been an hour, and I think that's a little longer than we were even thinking about. So I hope that everyone's enjoyed this and going back and forth. I plan on doing more of these and talking about technology and playing around with some of this stuff and seeing how it works. So James, thanks for joining me.
Yeah, it was a pleasure, Mike. I appreciate your passion for the tools and helping us express this in the market.
All right. Well, this will be available for playback on both LinkedIn and YouTube. So if you have any friends or family that you want to share it with and you're excited about it, send them the link and be sure to have them watch it. All right. Thank you very much. And we'll
thank you.
see you in the next one.